Hey everyone, let's jump right into this explainer and demystify the invisible engines that literally power our entire digital lives. Today we're taking a really close look at sort and search. At their core, searching algorithms are basically how computers find one specific piece of data buried in a massive digital haystack, right? And sorting algorithms, well, they logically organize all that data, whether that's alphabetically, numerically, chronologically, you name it. When we're dealing with data structures, efficiency here is absolutely crucial. It's the thin line separating a perfectly seamless experience from a totally frustrating one. So we're going to break down these common methods and see exactly how they make our searches so incredibly fast.
To give you a quick roadmap, we'll start with the hidden sorting engine, then move into the fundamentals of sorting data, and wrap things up with an algorithm complexity showdown.
Okay, let's kick things off with part 1, the hidden sorting engine. You know, we take internet speed for granted all the time, but under the hood, there is some massive heavy lifting going on. Think about the last time you searched for, say, a new pair of headphones on a giant e-commerce site. You hit enter and boom, thousands of results instantly. But then you do something that triggers a massive calculation. You filter that huge database by lowest price or maybe highest rating. How exactly does that happen without you having to stare at an endless spinning loading wheel?
Well, this right here really illustrates the real-world power of what we're talking about today. The answer? Highly efficient sorting algorithms. These invisible workers ensure that massive datasets, we're talking millions of products, are seamlessly arranged to exactly match your preferences, almost instantly. They are literally the difference between a snappy, responsive app and a totally frustrating shopping experience that you just abandon halfway through.
Moving right along, let's get into part 2, the fundamentals of sorting data.
Now that we know why this stuff matters for our everyday digital sanity, let's kind of open up the toolkit and establish the fundamental rules of the game. First up is this concept called stability. Basically, a sorting algorithm is considered stable if it preserves the relative order of equal elements in the final sorted output. To put that into perspective, if two elements in your dataset have the exact same value, their order at the end remains exactly the same as it was when they went in. They don't just magically swap places because they tie, their original sequence is strictly respected.
Next up, we have in-place sorting. This means the algorithm transforms the input using only a constant, tiny amount of extra storage space. Actually, think of it like tidying up a super cluttered room, but you're not allowed to move any of the furniture out into the hallway first. You're sorting everything right there, entirely within the original data structure, without needing some massive secondary storage space to pull it off.
Finally, let's look at comparison-based sorting. And just like the name implies, these algorithms sort elements by comparing them pairwise, matching them up directly against each other. Because they use this specific method, they actually hit a hard mathematical speed limit, which is a lower bound time complexity of O of n log n. But, and this is a pretty fascinating exception, non-comparison-based sorting algorithms can actually achieve linear time complexity. However, you can't get something for nothing, right? Doing that requires some very specific assumptions about the input data you're working with.
All right, this brings us to part 3, the algorithm complexity showdown.
So, the really crucial point here is that not all algorithms are created equal. They process data differently, they use resources differently, which brings us to the raw numbers. There is a massive contrast in how these perform, where n is simply the number of elements in our data set. When we break down the time complexity for best, average, and worst-case scenarios, it's pretty wild. An algorithm like insertion sort can hit a totally sluggish O of n squared in its worst case. That basically means the time it takes grows exponentially as you add more data. Selection sort and bubble sort, they also hit that O of n squared brick wall. But then, look at merge sort. It reliably holds steady at O of n log n across the board, best, average, worst, meaning it handles massive data sets so much more efficiently. Quicksort is also incredibly popular, hitting O of n log n on average, though, yeah, it can slip back to O of n squared in the absolute worst case. We also see algorithms like counting sort and bucket sort hitting O of n plus k, and radix sort operating at O of d times n plus k.
Ultimately, choosing the right algorithm is always this delicate balancing act. On one side of the scale, you've got time complexity. That's the pure speed of the algorithm across those different scenarios we just talked about. But on the other side, you have space complexity, and that's the amount of extra memory or storage required to actually run the thing. For instance, as we just saw, heap sort maintains a beautifully consistent O of n log n time complexity while boasting a tiny O of 1 space complexity. Merge sort? Super fast, but it demands an O of n space complexity. It's a classic trade-off. You're pretty much always trading memory for speed, or speed for memory.
Now, while we just looked at an entire toolkit of sorting possibilities, the true heavyweights we're really going to focus our attention on for this explainer are merge sort, quick sort, and counting sort. These three represent some absolutely incredibly powerful and very distinct approaches to organizing data. They balance those constraints of time and space in ways that quite literally run the modern web.
So here's a thought to leave you with. The next time you're shopping online and your search results miraculously reorganize themselves in the blink of an eye, take a quick second to appreciate the intense math happening right behind your screen. Ask yourself, which invisible mathematical engine, whether it's merge sort, quick sort, or counting sort, just won the race to organize your digital world? Thanks so much for joining me for this explainer, and keep questioning how our digital world is built.